All right, mic check. Ivan, can you hear me?
Yes, I could hear you.
Okay, I can hear you too. Perfect.
Dr. Chan,
Yes.
this meeting was already recording. I was the first one to step in the meeting, and it was already recording. So
Yeah, it starts recording when the first person shows up.
okay.
Yeah, because I have it saved to the cloud because I'm not using a personal laptop here, so I'm using basically the podium computer. And so in the past, what I've done is I've recorded it locally, and then I've had to wait for the recording to process. And so because this is this class ends at 8:15, I don't want to wait an extra like 30 minutes.
Yeah.
So I record to the cloud.
Yeah.
Because of that, it's just the first person that shows up. That's when it starts recording. So.
I was just worried that you're gonna get like an hour of nothing because maybe the person beforehand left it on recording. Sir, I have a quick question. Can I share my screen? It's about the grading.
Oh, sure. Yeah.
I have no complaints, but I am confused. I am confused about something. Thank you for allowing to share. Let me go to the grades. Okay. So can you see my screen?
Yes.
Okay, so I noticed one thing that's interesting was that I noticed that for assignment number 2, it went to Turnitin, and I'm not worried about that obviously because my work is original. However, I seem to have gotten a high plagiarism percentage because I copied and pasted the questions of the assignment to my homework, and
yeah, that's fine. That happens a lot in this class because I mean, first of all, everyone's kind of turning in the same thing. But also, if you're copying the questions from the, directly from the homework, then that's going to flag because everyone has that too. So, I mean, yeah, I do that just because, there's some cases where it's like 90, 95, 100%.
Oh yeah.
That's obvious.
It's suspicious then.
But then for most people, they're going to end up in the like 60, 70, even like I've seen 82, but I'm checking all those. So basically,
I have no complaints, and my question isn't regarding Turnitin. I'm just mentioning that in case this has something to do with my main question. Yeah. My main question is, I'm noticing that I have, assignment 1, assignment 2, and assignment 3, right?
Yeah.
But if you look at my screen, assignment 3 seems like, I click here and it says the assignment is dropped and will not be considered in the total calculation. Do you know why that is? Are you aware of that? Or
yeah, I'm aware of that. So basically, I set up the Canvas to automatically drop your lowest homework assignment. And so, right now, a lot of people in the class have, 100% in the class because, you've done all the assignments and you did the email. And so, there's no lowest one because they're all 100%. And so Canvas just chooses one to drop. And I think it does, you have to have a minimum of 3 assignments in the category before it drops something. So yeah, a couple other people have asked me that too, but yeah.
Thank you.
Yeah.
Yeah, that was my main question. Thank you for your help, sir.
Yep.
See, just for clarity, what I was thinking, I was like, maybe Canvas is dropping that assignment because it thinks like because of the plagiarism I got via copying the questions. That's what I was concerned about.
I see. Yep. No, they're unrelated. Yeah.
Thank you, sir.
It's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. Hopefully everyone had a good long weekend. If you're like me, you took it to catch up on work a little bit. All right, so today it's the only lecture that we're having this week, but thankfully it's an exciting one. So we're on our third ANSYS activity, okay, 3rd out of 8 in this class. But this one's interesting because it's going to be our last, I would say our last activity on the basics. Okay, so after this activity today, and after all the lectures that we've been having, I would say you kind of have a good grasp of kind of all the basics for ANSYS. Okay. And so like I mentioned before, after today, I would say you guys are ready to do kind of a more kind of independent project, which is going to be the midterm project. And so I've already mentioned to a couple people. So on Monday, what we're going to discuss is the midterm project, what that is, what you're expected to do. And then, you'll have about a month to work on it. Okay. All right. So, but for today, we're going to be just doing kind of an activity. And basically the point of today's activity is to basically get you familiar with how to work with assemblies. Okay. And so it's in reality, I don't think it's not that hard. It's just, I'm just kind of making you more aware of kind of the options that you have when you have multiple parts in your assemblies, more so than just one component. Okay. All right. And so the subject for today's activity is going to be a signpost. Okay. And so visually, it looks like a kind of one of those signposts that you see over the freeway that tells you, you're about to miss your exit, right? And so you have kind of a big rectangular sign supported by a cylindrical post, and then it's all kind of fixed into the ground at the bottom of the post. Okay. And so, like I mentioned, what's interesting about this geometry is that we have multiple components. The two main components here are going to be the sign and the post. Okay. But there's actually going to be a third component here. And it's almost like, I call it almost like a phantom surface. And so basically that surface is going to allow us to apply a boundary condition on one side of the sign. Okay. And so, that is also there to kind of show you that, sometimes if you want to apply a certain load to a geometry, but the geometrical features kind of aren't really allowing you to apply that load, sometimes you have to kind of create an extra surface in there to, to apply that load. Okay. All right, so the dimensions for the signpost are here, but that's kind of irrelevant because I give you the CAD file, but you can verify those measurements. Okay, and we have all the loads here as well. All right, so similar to the last activity, I'm going to focus mostly on kind of the new stuff, and so a lot of the kind of the basic things like meshing and applying the boundary conditions, I'll leave it kind of mostly up to you, and we'll focus on kind of the newer things in this activity. All right, so to get started, you can download the project instruction or the activity instructions from the website. And so you can go to assignments, go to assignment 3. This first link here is going to be the activity kind of specifications. And then we have 2 CAD files. And so the first CAD file is going to be the one that we're going to use in the activity. And then the second CAD file is going to be for an extra assignment on top of that. Okay, and so that's the plan for today. Are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get started. So go ahead and I need to download the CAD file here. Okay. All right, so let's open up Workbench. And just like before, let's go ahead and create a static structural analysis here. And then let's load in our geometry. So let's right click on geometry here and import. And then let's import the geometry that you downloaded. And so it should be solid signpost geometry base. Okay. And so the nice thing about this geometry is that it was actually created in ANSYS. And so there should be no compatibility issues whatsoever. Okay. So let's go ahead and double click that. And then automatically what you should see is that there should be a green check mark next to the geometry that tells you that your import was successful. Okay. All right. So before we jump into mechanical, let's make sure that we have all of the material properties that we need. Okay. So let's go ahead and double click engineering data. And you'll see that the only material that we have right now is structural steel. Okay. All right. So for this activity, we're going to need another material because one thing that I'm going to illustrate later is that when you have an assembly of parts, you can actually assign different material properties to each of those parts. Okay, so let's also add aluminum here, but let's do it in kind of the lazy way. And so we're going to use kind of the pre-built aluminum that's already in ANSYS. So to do that, let's go ahead and click on engineering data sources. And so it kind of looks like this, series of books right here. Okay. And so when you click on engineering data sources, it should open up another menu. And then from here, you should be able to add any kind of material that you want. Okay. All right. So there's three kind of menus here. So let me kind of lower the bottom one just so you can see. And so this top window right here, which is called engineering data sources, these are all the different sources of materials that you can have within ANSYS. Okay. And so we have ANSYS grant material data for simulation, which is super long. We have general materials. We have additive manufacturing materials, geomechanical, composites, general nonlinears, explicit hyperelastic materials, all good stuff. Okay. So the material that we want is inside general materials. And so if you left click general materials once, what that's going to do is that it's going to change kind of this middle menu right here. And so you'll have a lot more options available here in the middle. Okay. All right. And so if you scroll down this menu right here, you can see there's quite a few options. Not that much, but there's a few. So we have aluminum alloy, we have concrete, we have copper, we have FR4. Cast iron, magnesium, polyethylene, stainless steel, structural steel, titanium alloy. So there's a lot of stuff. Okay. And so to add one of these materials to your workspace to make sure that you can have its materials, what you have to click on is this plus arrow next to the material. Okay. And so for this activity here, we're going to make use of aluminum. Okay. So let's go ahead and left click on aluminum. And if you left click on aluminum, what you should see is that there should be a book next to that aluminum alloy now that's telling you that you added that material to your project. Okay. Yeah, question. You just click the plus arrow. You just click it once. Yeah. Mm-hmm. Okay. And so if you click on that plus arrow, you should see the book. And if you want to verify, you can left click on engineering data sources here again. And so that'll close this menu right here. And so if you close that, you should see that you have two materials now. And so you'll have aluminum alloy, which is the one we just added. And then we have structural steel, which is the default material. Okay. All right. And so if you're doing a project and you are using a material that's inside the library, I would actually recommend to use the ANSYS ones, or at least check and see what the properties are, before you go in and add your own material. And we can check and verify these material properties as well. So if you left click on the aluminum alloy, we can check on its material properties here. Okay. The nice thing about this is that not only does it add the linear elastic material, so we have the Poisson's ratio and the Poisson and the Young's modulus, of course. Okay. We also have the density, and you'll see today that that's actually going to be useful. We'll actually use the density for something in the activity. All right, and so was everyone able to add aluminum alloy using the engineering data sources? Any questions on this part here? Okay. All right, so now that we've added the material, let's go ahead and close this. And then let's open up ANSYS Mechanical by double clicking on model right here. Okay. Okay. All right, and so if you imported the geometry correctly, you should see the signpost. And so, dimensionally, it's a little bit different than the one in the picture because, the one in the picture is not to scale, but you should see something that looks like this. Okay. And the first thing that we'll look at here is the geometry section. Okay? And so you should have three objects there. So you should have a CAD file for excuse me, you should have a part for the sign. You should have a part for the post. Okay? And you should have this WX2 application surface with the question mark next to that. Okay? We'll come back to that in a second. We'll talk about what that question mark is. We'll first talk about what this surface actually is. But first thing we'll do is that we'll assign the material properties for the post and the sign. Okay. Right. And so when you're working with an assembly of parts, oftentimes those parts are going to be made of different materials. Okay. And so the first thing that you need to make sure when you're working with these assemblies is that you assign the proper materials to each part of the assembly. Okay. So let's start with the post. And so if you look at the project specification or the activity specs, you'll see the post should be made of structural steel. Okay, and so to check the material that your part is using, you're going to left click on that part in the geometry tree, and then you're going to check the details menu on the bottom left, and you can check the material assignment. Okay, all right, and so you can see right now that the post is being assigned a material of structural steel because that is the default. So that looks good. And so we don't need to change anything for the post because that one already has the materials that we need. Okay. Now let's go to the sign. And so the sign is actually made of aluminum. Okay. So let's go ahead and change this material assignment from structural steel. And so let's change that to aluminum alloy right here. Okay. So let's left click on aluminum. And then that is going to change our material. All right. So it's pretty straightforward. As long as you have the materials loaded into your engineering data, then choosing them for the parts is pretty simple. Yeah.
What's the square next to this?
Yeah, that's a good question. Yeah, people have noticed that square before too. And so if you click on it, you'll notice that a P shows up in that box. And so that P stands for parameter. And so basically what ANSYS lets you do is that it lets you do what's called design optimization. And so you can basically say that, I have this part, ANSYS, and I don't know what material, I don't know what the best material is going to be, but I'll let you choose. And so, if you mark this and then you use kind of the optimization features of ANSYS, then ANSYS will basically run lots of simulations and tell you which one is the best. Yeah. And so if you look at different parts of here, you'll see that kind of box next to a lot of things. So you can set different things as parameters. Yeah, we'll go over optimization later in the class. It's one of the cooler features in ANSYS. So I think that's activity 6 or 7. So yeah, we will definitely be going over that later. Yeah. All right, any other questions on this part here so far? Okay. All right, so that is the material assignment. Okay, so that's the sign and the post. Now let's go on to this WX2 application surface. Okay. All right, and so you can kind of see it on my screen a little bit, but when you click on WX2 application surface, you should see kind of the left side of this post here kind of light up. Okay, and if you kind of rotate around, you can see that this WX2 application surface is kind of like a thin strip, almost like a strip of duct tape that goes from the top of the sign to the bottom. Okay, and you can kind of zoom in, you can kind of see it's basically just a very thin strip. Okay, so if you look at it, its thickness is nothing. Okay. All right. And so a surface like this, I like to call it, I don't know if this is the official word for it, but I just like calling it this, I call it basically a phantom surface. Okay. And so it's a surface it's a part that's, not structurally, it's not part of the original geometry. Okay. So if you look at a typical signpost on the freeway, there's not going to be a very thin piece of material that runs down the side. Okay. So this strip here, you can almost say it doesn't actually exist in the real geometry. Okay. The purpose for the strip is to allow us to apply a loading in an interesting way. Okay. And so if you go back to the project the activity specifications, okay, if you look at this diagram here, we have this load here called WX2, okay? And WX2 is basically pushing on the signpost going from left to right, okay? Excuse me. And so what that load is that it represents the wind load. So when you have wind that's kind of blowing against the sign, then that load there kind of represents that, okay? Well, what's unique about this loading, I mean, part of what's unique is that it's a variable load. So we'll talk about that in a bit. But this loading kind of stretches up from the very top of the signpost all the way to the bottom. Okay. And so if you go back to mechanical, right? We know from previous activities that if you want to apply a load onto a part of the structure, you have to be able to click on that surface, right? And so, you know, you could click around all you want here. Okay. So you can try clicking on the post, you can try clicking on the sign, okay? On each edge. Okay. There's no natural surface on this geometry here that stretches from the very top to the bottom. Okay. All right. So nothing is going to give you that exact surface there. Okay. But you know, because of the way that this is loaded, and because of the way that we want to set this up, we want to apply a load that stretches from the top and the bottom. Okay. And so one way that you can accomplish this is that you can set up, or you can specify a phantom surface like this so that you can actually apply this load. Okay. And so if you click on this surface right here, you can see that this surface actually does stretch from the very top and bottom, okay, which normally would be impossible with just kind of the natural geometry of this CAD file. Okay. And so what this person did, or what the author of this CAD file did, was he created that surface so that we could apply that load. Okay. And so this is a fairly common technique because a lot of times you're going to want to apply a load, but you don't want to apply, but you want to apply it on a surface that may not be natural to your geometry. Okay. And so this is basically kind of what you would do. Okay. The only thing that we have to specify here, and the reason why we have this blue question mark, is that because it's kind of a phantom surface, we don't actually want it to have any physical thickness. Okay. And so what this person did was he specified it as kind of like a pseudo 2D surface, or a pseudo shell surface, okay, where you have to specify the thickness of the surface manually. Okay. And so if you look down in the details window, that's the thing that is wanting you to specify.
Dr. Chan, I have a question.
Yes.
So, from my understanding, whoever designed this CAD or already inputted that quote unquote phantom surface. Yep. Will we learn how to do that ourselves eventually?
Yep. Yep.
Okay.
Yep. I have a handout for it. It's online. And yeah, we'll go over it, before we talk about the project.
Sounds good.
All right. And so the main thing is that we have to specify a thickness. Okay. Excuse me. Because what ANSYS thinks, right now, ANSYS doesn't know that this is a phantom surface. Excuse me, sorry. And so only we, the users, know that this surface actually shouldn't exist in the geometry. Okay? And so when ANSYS is asking us for thickness here, usually for these surfaces, you should just set something arbitrarily very small. Sorry about that. My wife is beautiful. I love my wife. Hopefully that cures my cough. Okay. All right. And so for this, you can set almost anything for this thickness, but I'm going to set something kind of arbitrarily very small. And so I'm going to set it to be equal to 0.001 inches. Okay. All right. And so, that is super thin. Okay. But remember, this surface shouldn't actually exist. And so we want to give it a thickness so that it doesn't, really exist. You want to be careful here a little bit though. You don't want to set it too small. And so you want to set it small enough that it's not going to be an issue, but not so small that it causes other numerical issues. Okay, so something that like maybe 1 inch, 0.1 inches, 0.001 inches, something around there is probably good. Okay, question?
So you said
0.001. Yeah, it doesn't really matter. You can do 0.001, you can do 0.1, as long as it's small enough so that it doesn't matter. Yeah, I just like 0.001 just because it's really small. Right. And of course, you know, this, because this strip here, it's registered as a separate part in the geometry. Technically, you can also give it a material, but because it's so thin, it's not actually adding any structural strength. And so it doesn't really matter what material you can assign it. So you can give it structural steel, you can change the lumen if you want to. You know, it doesn't really matter because it's so thin that it's not going to add anything of substance. All right. Any questions on this? Okay. So that's the geometry. Right? Step out to get a drink of water in a second. All right, let me get to a point where you guys can kind of work on it, and then I'll go from there. Okay, and so first thing when you're doing assemblies is that you need to assign materials to all the parts. Okay, so that part I think fairly obvious. The next part that we'll talk about in assemblies is connections. Okay, and so when you have multiple parts in an assembly, you need to define to ANSYS how these parts are going to interact. All right, so let's look at one contact region here to kind of illustrate what I mean. Okay. And so for me, it's contact region 2, but for this part, it doesn't really matter all too much. And so what you'll notice is that if you kind of expand this section for connections and go to contacts, when you click on each contact region, it should show you the 2 parts that is being in contact and kind of the area where they're in contact with. Okay. And so for this contact region 2, this is the contact between the sign and the post. Okay. And so if you look at this, we have these 2 surfaces here, which are, interacting with each other. Okay. All right. So ANSYS gives you the option to basically define how this interaction is going to go. Okay. And so the main thing that you'll see in the bottom left is the type. Okay. And so the type of connection will basically tell you how those parts are going to interact. Okay. So the default is bonded. And so what a bonded contact basically means that your 2 parts, they're basically going to be super glued, they're going to be welded together. And so those 2 parts are effectively going to act as one. Okay. And so for this particular case, we want it to be bonded because we want the sign to be bonded to the post. Okay. So bonded basically means, no separation, no sliding, no nothing. Okay, so then basically, the mesh nodes are on top of each other and they're basically going to act as one. If you look at some of the other options here, you can see kind of what other options you have for kind of more complicated assemblies. Okay? And so you can have a contact called no separation. And so that basically means that your 2 parts cannot be separated from each other, but they can slide. Okay, and so that would be a case if you want kind of a, your 2 parts to just always be in contact, but can still slide by each other. Okay. You can have a frictionless surface, and so a frictionless surface basically means that there's no friction between them, but they can't separate in that case. Okay. And then you can also have rough and frictional, which are kind of 2 versions of kind of the same thing. The two surfaces can kind of slide past each other, but there's going to be some resistance. And that resistance is defined by a coefficient of friction. Okay. Right. I will say that, for most static cases, most of the time you're going to pick bonded support because, for most static structures, you don't want your parts kind of sliding past each other. But once you start getting into dynamic simulations, which we'll get to, later on in the course as well, there will be instances where you do want to change the contacts. But for now, for this activity, we're not going to change these contacts. And so we're going to keep it as bonded for all 3 regions because, we want them to be bonded together. But, that's another thing that you have to kind of take into account when you're doing assemblies is to kind of make sure the contact regions are exactly what you want to. Okay? And for certain situations where you're kind of, and you'll see this in activity 4. So for certain situations, you may have to create the contact regions yourself. Okay? But we'll kind of cross that bridge once we get there. Okay. For now, I just kind of want to show you what the contact regions are and what bonded means, because that's something that's kind of important. Okay. Okay. All right. Any questions on this so far? Okay. Another thing that I'll show you at this part, which I kind of forgot about until I looked at the activity, is that you can rename a lot of things in ANSYS. Okay? And renaming, as mundane as it sounds, is actually, really, really useful. Okay? It may seem kind of trivial for a case like this where we only have 3 parts and 3 contact regions. But when you start working with kind of more complex assemblies, with maybe a dozen parts, or maybe even dozens of parts, it starts to get it starts to become a lot to keep track of. And so to help you kind of keep track of this, sometimes it's really useful to help kind of rename some things so that it's easier to refer to. Okay, because if you just look at this list, and you can kind of see me, you could kind of see me struggling with it a little bit earlier. When I see contact region 1, 2, 3. I have no idea what those are referring to, right? So I had to actually click on them to actually see what they're referring to. Okay? And so what you can do instead, you can rename these to kind of make them more useful to you in the long run. Okay? And so for instance, for this contact region here, I can see that it's the contact between the phantom surface and the sign. Okay? And so if I rename this, and you can rename a couple ways. So you can right click on it and click on rename. Okay? Or you can see that the keyboard shortcut for renaming is F2. So that's usually what I prefer. All right. And so if we rename this, we can call this phantom sign connection. Okay. Contact region 2 right here is between the post and the sign. That's what we call this post sign connection. Okay. And then contact region 3, we can see from the image here is between the phantom surface and the post. Okay. So again, it's not something that you have to do, but it is useful, especially once you start to get to once you start doing more complicated ANSYS stuff. Okay. All right. So let's go ahead and move on to the meshing. Okay. All right. So I'll let you guys work on the meshing for a little bit, but let me show you kind of what I'm expecting. So one nice thing about assemblies is that you can apply different meshing settings to different parts of the assembly. Okay. We talked about this a little bit, I think, before activity 2. And so we call this mixed meshing. Okay. So let's do this. And so let's create a method object and a sign and a sizing object. Okay. And so I'm going to create one for the post and one for the sign as well. Okay. All right. So for the automatic method, let's go ahead and apply this to the sign. And for the sizing, let's go ahead and apply it to the sign as well. Okay. And same thing for the post. And so for the post, we'll have one there, and sizing for that as well. Okay. You can rename these. And so usually I like to do this. This one's useful. And so this is sign method. This will be sign sizing. The post method. Let's be post site. Okay. So with this, you're free to change your mesh settings for each part of this assembly. Okay. And this right here is a good example because, if I look at this assembly and I look at, in terms of, how I expect the simulation to go, that's going to tell me how I'm going to mesh this, this geometry. Okay. All right. So first, for the method, the main thing you can change for the method here is the shape of the elements, right? So we have two options. So we have hex dominant and tetrahedrons. Okay. And so, if you look at the side of the geometry and you look at the side of the post, both of those have pretty different geometries, right? So, you should, based on our lectures on meshing, you should be able to determine, what's kind of the best shape or what's the shape that's going to work best for these parts. Okay. Right. And then for the sizing as well, right? Remember, we talked about the mesh size is directly correlated to the accuracy of the simulation. Okay. And usually, when you're running a structural simulation, you want to have the most mesh density in the region where you expect the stresses to be the highest. Okay. And so I want you to look at this geometry here. Think about, you can use the figure in the specs to kind of help you out in terms of how it's loaded. Think about which part of this geometry is going to be bearing most of the stress or bearing most of the load. And then I want you to add most of the element density in that area. And then maybe the other part of the geometry, you use a coarser mesh. Okay. All right, so I'll let you guys play around with that for a little bit. I'll be back in like 5 minutes. I just need to go run to the drinking fountain to get a drink of water, and then we'll come back after that. Okay, so I'll go ahead and specify the method and the sizing for each of the parts of this assembly, and make sure that you kind of choose them with a little bit of thought. Okay. I'll be right back. Yes. Yeah.
Dr. Chan, I have a question.
Someone's asked me a question in class. I'll come back to you in a second.
It sounds good.
I don't specify on the worksheet. So, and so it's, I'm not looking for a specific number for the mesh sizing, but there should definitely be a part of this geometry that has a fine mesh. So the element should be small. And there's definitely a part of this geometry that should have a coarser mesh. And so that's kind of what I'm more looking for in this activity. You can use the English units, and so I think the default right now is English. Yeah, and so you can for right now, for the mesh sizing, the units don't matter too much, but they will for the loading. Okay, yeah, it should become more quick. And remember, the mesh settings you can change later. And so probably once you see the simulation results, you may want to change the mesh after that too. So, and that's okay. And so, a lot of FEA is it's very iterative. There's a lot of times you'll try something and then you're like, oh, maybe I shouldn't modify the mesh here. And that's totally normal. That's most people kind of go through that process. Yeah. All right, Ivan, go ahead.
Thank you, sir. I was looking at the case that we're working with, and you mentioned to focus on the area where higher stresses are expected to occur, and I'm thinking about this solid mechanics for obvious reasons. And I have a simple question that I feel like I should know, but I don't at the moment. So there's the area where the stresses are high, right? Is that area the same area where deformation is also expected to occur, or are those two areas completely different? The area where the high stresses occur and the area where the highest deformation occur, are those areas in the same area, or are those two different areas? Or
it's a good question. And so the way deformation is computed in ANSYS is that it takes kind of the original position, and so this is kind of the original configuration of the signpost.
Yes.
And then after you apply all the loads and constraints, then it's going to deform into a certain way to the final configuration, right? And so the deformation is simply just a subtraction between the original configuration versus the final one. And correct. that is the deformation. Right? So and so it could be, in certain situations, especially situations where you have a lot of bending.
Yeah, that's what I'm thinking about. Like in cases of bending, is because let's say we have cantilever beam, the highest deformation would be at the tip, but the highest stress would be where it's supported, right?
Yep.
Okay. And in that instance, highest deformation, and highest stress are in different areas.
Exactly. Yep.
Okay. Thank you, sir. I'm just trying to make sense of all this.
Sure. Yeah, no, it helps to talk through it. So yeah, definitely good.
Thank you, sir.
Yep. Question, yes.
Just a quick question. How do you reset the layout?
How do you reset it? So usually I go up here to layout and then reset layout right here. It's in the top right.
Professor.
Yep.
So for the sign for the method,
Yep.
I'm still not entirely clear which is the best method for the mesh for the sign.
Yep.
Tetrahedron, hex dominant, sweep, multi-zone, Cartesian, layered tetrahedrons. Based on our last assignment, it seems like we should be doing hex dominant a lot and less otherwise.
Yes. Yeah. So your main two options here are going to be either tetrahedrons or hex dominant. So the rest, we'll get to the rest later, but the only ones that we've really learned so far are just the tets and the hexes. And so tets, remember, are these kind of pyramid looking elements that look like this.
Right.
And their main benefit was that you can use tets to mesh any geometry. So they're going to work for anything. The downside to them is that they don't really fill the areas very efficiently. So what you see kind of a lot is that if you mesh with tetrahedrons, then it takes a lot of elements often to fill a space. And a lot of times those elements aren't really, it's a little bit inefficient. And so, it takes more elements to do that, and it's going to drive the cost of your simulation up. Hexahedrons, on the other hand, are these kind of, they look like bricks, and sometimes people call them brick elements. And so the nice thing about hexes.
So for something that's square like the sign.
Yes, exactly.
Hex dominant would be perfect.
Exactly, right, yes.
Okay, and then for the post, hex dominant is preferred.
Yep.
But if that doesn't work, well,
right.
Which one is better for square stuff and which is better for round stuff is what I mean.
Exactly. Yeah. So you can get hexes to work on round things. And actually for this cylinder, it's, even though it's round, it still has a very nice structure. Like, it's pretty well structured. Like, it's just a rod basically. And so, a lot of students in the past have gotten hexes to work on the rod as well. And if you can do that, that's great. But typically for kind of more curved geometries, more complex geometries, a lot of times you're kind of forced into using tetrahedrons. But definitely for the sign, because the sign is literally just a gigantic rectangle, then hex is definitely the preferred option for that.
Okay. Free mesh, free face mesh type, quad tri or all quad. I'm a little off on the differences.
Don't worry about that too much. And so just choose the bulk element shape. So it's tetrahedron or hex. Everything else you can leave on default. Yeah.
Okay.
Yeah. All right, question, Mario.
Yeah, someone asked a question in chat, and I'm just making you aware of it.
Yeah, I'm getting to it right now. Yeah. All right, so question in the chat. So since adding refinement makes the element shape triangular, is it worth adding refinement if it loses the rectangular type elements? Yeah, that's a really good question, and that's a trade-off that you have to kind of think about in a lot of situations. So what Mario was referring to is that if you excuse me, if you remember from activity 1, an extra meshing option that you have is that you can add mesh refinement in a certain area. Okay, and so that will refine the mesh relative to the areas around it. But one downside to that is that it switches the element shape to triangular versus rectangular. And so the reason that exists is that for a lot of geometry, sometimes you don't have a choice, and so sometimes you have to use a triangular mesh just because of how complex the geometry is. And so for those situations, it doesn't matter. Adding the refinement is going to be a net positive because it's going to give you a refined mesh. But for cases where you have a good rectangular mesh, it's kind of debatable on kind of which one is better or not. Personally, I would say in most cases it's better to use the rectangular mesh, and then instead of using refinement, you can use a local sizing option instead. And so let's say that you wanted to refine the mesh kind of up here. right where these two connect. Okay. Not saying that that's good. That's not saying that's a good decision in general, but let's just say, for instance, we want to do that. And so what you can do instead is you can add an extra sizing object, and you can, maybe add a phantom surface, if you really want to be fancy, but maybe you just want to click on just this part right here. Okay, just this edge. Okay. And so what you can do there is that you can change the size from there. And so you can kind of create the same effect as mesh refinement. It's not quite the same. It doesn't kind of refine it as well as the mesh refinement. But oftentimes it does do a good enough job. And so with the sizing object, you are able to retain the same shape as before, without kind of, while still refining the mesh. And so personally, that's kind of what I do a lot of times is that I try to preserve the shape, because the hexes are really valuable if you can use them. And so I personally prefer to use the hexes, but different people in the field have different thoughts on that. So yeah, it's definitely not a clear cut. Question, yeah.
Yes, I mentioned stuff.
Let me go back and check. Now that computer just might be cursed. I think you might that computer's had issue before. If you guys are done with the mesh, you can go ahead and move on. So actually everything else is pretty well outlined in the activity report. So you can do the loads and the constraints and stuff like that. Yeah. Let's stop. What are the sizes? That's pretty small. Yeah. So it's not getting stuck. It's just trying to. This is a big one. It's huge. It's huge. So it's about this 4 inches. 4 inches tall. So do 0.1. It's about 4,000. I would start with something bigger. Oh, even I would start with, if you want. It's the default sizes. I would usually start in that one. Okay. If you find it was small. Exactly. Yeah. So each part's different. So I mean, for these activities, it's a little bit disorienting because I'm getting the parts. So you really have no idea how big they are. But in reality, you kind of have an idea how big. Okay. Yeah. All right. Yeah.
So how?
Yeah. 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 There's no golden ratio. I'm not looking for a specific ratio. It should be very visual. So you'll see what you actually run the simulation, where it's stressing or concentrating. So that'll tell you where the mission is. And you will also see parts of this geometry with stress based. So in those cases, you can so I would say if you got a mesh, I would say just go mesh. Go ahead and move on to the and then once you run the simulation, it should become pretty obvious. I would say to start with, that's okay. But for the final activity or for the final report, I do want to see kind of a visual difference in the size of one part versus the other part. Okay. So once you run the simulation, it should become pretty obvious. There will be a part where the stress is super high, and another part where the stress is 0. And so where the stress is super high, that's where I want to see the most dimension. And when the stress is 0, okay, yeah, I would say maybe try with the automatic first. Run the simulation, and then you can use the simulations. Exactly. Yeah, but for automatic or first, it should with automatic. Yeah, let's do it. Okay, so let's go ahead and move on. All right, and so what I was telling people in the class too is that I'm kind of stopping around to kind of help people, but if you want to move on, I think with this starting with this activity, I think most of kind of the explicit instructions are in the document, and so definitely feel free to kind of move on from here. Okay. Okay, so the next part is the loads and constraints. And so we have actually not that many loads. Okay. All right, and so we're going to do a new load today. And so we haven't done this load before. Okay. But a lot of times when you're talking about, especially for the bigger structures like this, the weight of the parts itself actually becomes a significant load. Okay. And so the nice thing about ANSYS is that there's kind of an easy way to supply the weight. Okay. And so this is different from the original diagram. So if you look at the original diagram here, the weight of the post and the weight of the sign, we actually have as separate forces, but ANSYS has kind of an easy way to do it kind of all in one. Okay. Okay. And so if you come back to ANSYS right here, right? Remember, to add loads and constraints, we need to right click on static structural here and then go to insert. Okay. All right. So the first load that I'm going to add here is called, I need to find it first. There it is. Okay. It's called standard earth gravity. Okay. All right. And so what standard earth gravity means is that, for each of the parts in the assembly, okay, it's going to compute its weight based on the density that's supplied in the material properties, and then apply that weight as kind of a body force throughout the entire structure. Okay. All right. And the nice thing about standard earth gravity is that it's almost like a toggle. So you can either turn it on or off. Okay. And so you can right click on standard earth gravity, and then now it's automatically being applied. So we don't even have to select any parts of geometry. We just said that we want gravity being there. Okay. And so for activities 2 and 3, activities 1 and 2, we've actually ignored gravity at this point. But because now we have a much larger structure than what we've been doing before, gravity is going to be much more significant because these parts are pretty heavy. Yeah, question. It should be near the top. And so when you right click on static structural A5, you go to insert. And so it should be kind of near the top right here. Yeah, I don't see it anymore because I've already added it, but it should be right under acceleration. Yeah. Okay. And so that's standard earth gravity. Okay. The next 2 modes that we need to add here are the wind forces. Okay. And we have 2. And so we have the wind force that's acting on our phantom surface. And we have another wind force that's actually being applied, on the middle of the sun. Okay. All right, so let's do the wind force that's on the middle of the sign first. Okay, and so it's really hard to see, and actually, if you don't mouse over it, it's actually impossible to see. But what the author of this CAD file did was he put like an extra point in the middle of the sign. In fact, it might be on the other side here. We have to add the force first. Okay, and so that point is kind of like it's almost like another phantom surface, but this is like a phantom point. Okay, and so you can also add points into your geometry for the sake of load application like this. Okay. All right, so let's go ahead and right click insert. Okay, and then let's go to let's create a force object. Okay, and so this is going to be a force load. And then let's find the geometry that we want to apply this on. So you're going to have to search around a little bit for it because it's not obvious. But if you kind of hover your mouse around kind of the middle of the sign, eventually you'll find kind of a point that's on there.
Dr. Chan.
Yes. Is
this a feature of ANSYS where ANSYS can tell you the centroid of an object? Is that what we're doing? Is that point the centroid?
It is, but it's not something that ANSYS told you. It was something that the author of this CAD file added manually.
Oh, okay. So if we were doing a completely new geometry, we would have to specifically state the centroid of the.
Exactly.
Okay. Thank you, sir.
Yeah. Yeah, and if you're having trouble finding it, you may need to switch your selection mode. And so you can do Control P on the keyboard, or you can click on this button here on the interface called vertex. Okay. All right, and so once you find it, it's kind of in the middle of the sign, kind of right here. Okay, so you're going to go ahead and click on it, and then you're going to click on apply right here. Okay. All right, and so that tells ANSYS that we want to apply a force onto the middle of the sign. Okay. All right, and so the force that we're going to apply has a magnitude of 8,000 pounds, and it's going to be applied in the Y direction. Okay. And so just like we usually do, let's switch the force definition to components, okay? And then we're gonna apply a force of 8,000 pounds in the Y direction. Okay, so just like that. It should be positive because it should be going into the sign. Yeah. But due to the symmetry, I think it shouldn't matter. So if you do negative 8,000, it should be okay too. But the way it's defined here, I have positive 8,000. Yeah. Just a regular force. Right. Yeah. All right. And so that's how you can apply a force at a point. Okay. I would say this is not the best example of doing this, but there are situations where you would want to apply a force that's directly on a point. Here, it doesn't really make that much sense because we have kind of a nice, big, wide, sign surface here. Okay, and especially the fact that this force here is representing a wind force. That wind is going to be applying force pretty equally across the sign. And so, to me personally, I think it doesn't make that much sense to apply it as a point. But I have it in this activity just so that, just to illustrate to you that you can apply a force at a point. And that's kind of how you do it. Okay?
Dr. Chan.
Yes.
For this instance, would a pressure force also be suitable because it's a force per area?
It would be, yes, but you would have to compute the force kind of manually, or the pressure manually, because it's like we talked about last time. So pressure and force can kind of be interchangeable, but you want to make sure that the magnitude of the force overall is going to be the same. Yeah.
I see. Thank you, sir.
Yeah. Mm-hmm. Okay, so that's the point force. The other thing that we need to do is we need to apply the wind force that's on the side. Okay, so that's kind of the whole point of this phantom surface. Okay, so let's go ahead and apply this as a pressure. So let's right click on static structural A5 and insert a pressure. Okay. And for the pressure, we're going to select our phantom surface. Okay, so go ahead and mouse over that. Click on that. This one. Okay. And so your our application surface for this pressure force should be the phantom surface that goes along the side of the signpost. Okay. Okay. And so what's unique about this pressure force here is that it doesn't have a uniform magnitude, right? If you go back to the project specifications here, you can see that the magnitude of the wind force has a higher magnitude up top and a lower magnitude on the bottom. So it's basically like a ramp force here. Okay. And so ANSYS has a way to apply that, okay? And the way we do that is basically the same way as you applying functions in Microsoft Excel, okay? All right, but before we do this, we need to make sure that we're in the right unit system. So, when we're applying this force, we're basically gonna be inputting a function. And so ANSYS should, ANSYS needs to know that we're applying this function in the right units, okay? And so when you go to units here, you want to make sure that you're on this kind of last option right here for US customary that is in inches, okay? And that basically tells us that our magnitude of the force or magnitude of pressure is going to be in PSI, okay? And so before you input anything into the function area, make sure that you're in US customary under inches, okay? All right, any questions on this? Good. Okay, all right, so now that that's done, let's go ahead and input the magnitude of the force, okay? And so when you want to add a spatially varying force, okay, you're going to have an equal sign, okay? And so that equal sign there basically tells ANSYS that you're going to input a function, okay? And it's complaining because I didn't actually do that, okay? I just wanted to circle it just so you know, okay? And then from here, you can input a function. And so some of the variables that you have available to you are going to be the X, Y, and Z coordinates. Okay? And so in this case, since we want to have the force vary in the Z direction, we're going to have a function of Z. Okay? And so the function that I'm going to input here is 0.1 multiplied by Z. Okay? And so I'm going to go ahead and hit enter. And so what that's going to do is that it's going to change the magnitude of the force. Okay. Maybe it's just not in this version, but in other versions, sometimes when you click on this, it should show you the magnitude of the force. Yes, the maximum minimum, not here, but shows on you. Okay, good. Okay, so it should show on yours, and so it should have a maximum magnitude of about 43.2 psi. Okay. I'm not sure why it's not showing on mine. Probably because I did that error earlier. But if you inputted this function correctly, it should have that magnitude. So actually, let me go ahead and delete this. I'm gonna try making it again one more time, just so you can see it. So you can kind of see it down here. For some reason, it's not showing up on the figure. That's okay. Okay. Yeah. Okay. Yeah, I'm not sure why it's not showing up there. That's kind of weird.
Professor, your mesh is not created yet.
Oh, that's true. I haven't created the mesh. Thank you for that. There we go. Okay. Thank you for that. Yeah, so my mesh is kind of ugly because I didn't change the settings, but probably hopefully yours looks different than this. Okay. But you should get a maximum pressure of about 43.2 psi. Okay. All right, and so the last thing we have to add here is, of course, our fixed support. And so I'll go ahead and give that one to you too. And so we're going to add our fixed support here. Okay, we can't run a structural simulation without a fixed support. And for this one, it should be pretty obvious, but the signpost is going to be attached to the ground. And so we want to fix it on kind of this bottom part of this post right here. Okay. Okay. All right, so now that we have the loads and constraints, we have the mesh. I'm going to go ahead and add in our results. So let's go ahead and look at the total deformation. Let's look at the equivalent stress. Okay. Yeah, the bottom face down here is the fixed support. Yeah. Okay, so I'm going to go ahead and run the simulation. I think in the activity document, I give you a few more result fields, but and so make sure that you're doing all those result fields. But I did want to run it first just to kind of illustrate to you kind of what I was talking about earlier. Okay, so I'm looking at the equivalent stress field, and actually let me turn off the mesh here so you can kind of see it a bit better. There we go. Okay. Okay, and so when you look at the equivalent stress solution here, it should look something like this. Okay, and so if you look up in the sign, right? If you look up in this area right here, you can see here that we have zero stress. Whereas for the post, you can see that we have a very large concentration of stress right here. And so that should tell you kind of how you should design your mesh. Okay? And so generally speaking, when you have a finite element simulation, you want to have a high concentration of elements where the stress is going to be the highest. Okay. And so from these results, we can see that, we should put a lot more elements in the post because that's where the stress values are interesting. But in the sign, which has no stress at all, we're kind of more free to course in the mesh right there. Okay. Yeah, question.
Problem when you justify keeping our default while trying to.
Exactly. Yeah. Yeah. And you can even do more coarse than the default too. And so you can even make the elements bigger than the default for the sign. Because ultimately it doesn't. It's just there to add weight, basically. Yeah. Mm-hmm. Yep. All right, and so that's the activity. So for the last 15 minutes, I'm mostly going to let you guys work and come around and answer individual questions. But I did want to go over the last parts of the activity just so that we're all kind of on the same page. Okay. Okay, and so we basically did problems 1 through 4 mostly. There's some parts you have to explain, especially in problem 1. Okay, but we kind of walk through those parts together. Okay, and for problem 4, I also want to see kind of the normal stresses as well as the shear stress. Okay, so make sure you have those. Okay. All right, problem 5. So problem 5 is, I call it post design. Okay? And so now that we have the simulation results for the post, okay, we're now free to kind of redesign the post to make it more stable. Okay. Right. And so if you look at these results here, you can see, well, at least for my simulation, we're getting a maximum stress of about 27,000 PSI. Okay. Probably for your guys' simulation, you're getting a different stress because your mesh looks a lot better than mine. But you're getting a fairly high stress down here. Okay. And so for problem 5, I want you to change to the geometry of the signpost, okay, so that your maximum stress is lowered. Okay. But I also don't want you to change the overall dimensions of the signpost. Okay. So it should stay the same height and it should stay the same width. Okay. And so, you can't make this sign shorter than it is because, otherwise cars are going to run into it as it's going under the freeway, right? But some things that you can change is that you can change the thickness of the sign. So you can change the sign to be, a little bit thinner, okay? And so that, of course, is going to shave some weight. And so that should reduce the stress, okay? Another thing you can do is you can change the diameter of the post, okay? You can also change the material of the sign. And so if you wanted to change the material maybe to something less dense, okay, that's another option for you. Okay. Or you can do something else. And so, I would say those 3 are kind of the main 3 that you can do. But I want you to change something in the geometry or the material. Okay. And so if you want to change the geometry, you're going to have to go back to design modeler here. Okay. So you have to edit this geometry in design modeler. And then from there, you can change the dimensions of one of the parts of the assembly. Okay. Okay, so that's problem 5. And so I want you to change the geometry, rerun the simulation, and show me that the maximum stress did go down. Okay. Problem 6, I want you to think of 2 different other loading scenarios. Okay. And so the loading scenario that we've done so far is a fairly basic one. And so we've have the weights of the sign of the post, and we have a couple wind forces. Okay. I want you to think of 2 other scenarios that the signpost might be subjected to, and then simulate those as well. Okay. You can do this on the original geometry, or you can do this on your redesigned geometry. It doesn't really matter to me. Okay. And so, maybe some instances that you can think of, maybe you have, a really fat bird or something sitting on the edge of the sign right here. And so that's adding an extra weight on the sign. Okay. So that would be another scenario. Maybe you have, maybe a car ran into the sign on the bottom. So you add an additional force down here. Okay. So that would be kind of another scenario. So, be creative. And so, I want you guys to kind of get into this habit of, thinking of not just the default kind of scenario that your geometry is subjected to, but what are some additional things that you can think of as well. Because, like we discussed before, kind of the benefits of finite elements is that you can easily simulate all these alternate scenarios, and it's very easy to do. Okay. And so, and this is something you'll have to do for your midterm project as well. And so, trying to get into this habit of thinking of alternate scenarios and simulating them is a good habit. Okay? So have some fun with this, be creative. I told my undergrads last semester that, when you're doing this part right here, think of a story. And so if you're coming with another scenario here, tell me a story about what's happening. It could be as funny or as ridiculous as it is, maybe, maybe Superman, ran into the sign for some reason, or maybe Batman is repelling from the sign or something, So be funny, be creative. It's always more fun when I'm grading these to read kind of funny scenarios like that. And then once you have those results, I want to see the total deformation field, the normal stress, and the maximum shear stress. Okay. All right. Problem 7 is just a summary. Okay. So just like the previous 2 activities, I want you to summarize your results. Okay. And then problem 8 is kind of the extra assignment. And so I gave you another CAD model for this activity. And so this assembly.step is a CAD model of a chair. And so I want you to go through and run the finite element analysis of that chair. Okay. And then there's kind of detailed instructions on how to do that down here. Okay. But I'll kind of save that for you guys to do later. All right, any questions on the rest of the activity? Okay, all right, so we have about 10 minutes left, and so I'll kind of make my round. So if you have any other questions on the activity, I'll go ahead and do that. If you're on Zoom, if you have questions for me, you can drop a question in the chat and I'll come back and answer it. But, of course, you guys are, at this point, you guys are free to go. And so, in case you guys are heading out right now, thank you guys for coming this week. I know it was a shortened week because of the holiday, but, I appreciate you guys coming out. And I hope you guys have a good weekend. And I will see you on Monday. And remember, Monday, we're talking about the midterm project. So Monday is definitely a good day to come. Right? All right, so I'll see you guys.
Thank you, Dr. Chan.
I added.
Okay, good.
So it'll convert the whole.
Exactly. Yeah.
So is there?
Yeah. So, no, if,
The better way would be to kind of section off the model.
Yeah. Yeah, so it's definitely a trade-off. And people definitely have different opinions on this. So I wouldn't say that there's a uniform opinion. Because hexameters are definitely superior. That's, for me, I would prefer to keep those because situations where you can use hexameters in practice are actually pretty rare. And so if you have a geometry where you can use hexes, I would say keep. Doesn't have to. But that's people that think element size is kind of the most determining factor, and so there's no right answer. So I would say that generally speaking, if you're going to use refinement, leave refinement a bit more than if you just use hexes by itself. Yeah. Okay. Maybe that's let's check. Yeah, because I used to do that manually in the activity, but I wanted to use this activity. I did add one of these. Is that why? Let's check the. Oh, shit. No. Oh, okay. Let's do this. Let's do. Okay. I'll go ahead. Oh, you added it and then and then you changed it. And then I changed it. Oh, okay. That's mostly the same. Oh, okay. I think this is you have to specify this 2 phases. Oh, it should just be one. It should just be the. I think it might have been doubled up at first. There you go. Yeah. Yeah, you want to be careful. It's sometimes it's such a smallest thing. Sometimes big difference. Okay. Yep. Yeah. No, unfortunately not. No. I wish because it is really annoying. I know. Super annoying. I hate it. Yeah, I know you asked that before. It looks like that's just
Yeah, we'll get to continue that first. It's just that we skip for this.
It's not, full one, it's super normal. Full one.
Yeah, those are.
It's one thing, it's one thing they move on to us.
For example.
Yeah. Honestly, like it is useful in practice to have this, to be able to change the dimensions. Because you'll see later, someone asked this before too. Later on, we're gonna do an activity called optimization. So you can actually have answers to optimize what's the best approach. You're gonna go through that technique. That's why it adds weird. That's high. And so, that the optimization is really nice. The data is just too nice. That's better. It's okay. As long as it's not just one dimension, it's just for this activity. For reality, yeah, you can have that. Then for this activity. Okay. Oh. Yep, no problem. See you next week. All right, Zoom people, I'm back. All right, question. All right, question, is it okay to put the fixed support just on the bottom face of the cube? Yeah, that's fine. That's what I did. So I just put the fixed support on just on the very bottom face. Yeah. If you want to add more stability, you can do the sides as well, technically, because that's, you can say that this part here is underground, but it shouldn't make that big a difference. So as long as you have just the very bottom face, then that's fine. Yeah. Yep.
Dr. Tran?
Hey, Chris, what's up?
Yeah. What load should we apply to the sign in terms of the force? I missed what you said, and
Yes. So the sign has a wind force of 8,000 pounds, but it's applied onto this kind of small point here in the middle.
okay, the point I understood, I just didn't know how much.
Oh, okay, yeah, it's 8,000 pounds.
I'm rocking ANSYS 2023.
Yep, that's fine.
And for the pressure where we did the 0.1 times Z, just above the magnitude, it says loaded area deformed.
Yeah,
The
that's fine.
instructions don't have the deformed. Should we worry about that?
No, just leave it on the default. So I think on the instructions, the instructions actually were probably done in like 2019 version.
Yeah.
Well, I think it must be a new thing that they added, but I think if it's there already by default, then that's what it was before. So yeah.
Okay.
That's fine.
What's the difference between initial and deformed? Do you know?
That's a good question. That's something new that they added. So I don't know exactly what they mean by that.
Okay.
And so I think I just kind of based off reading that, because when you apply the load, the whole geometry is going to deform, right? And so I think when you're applying that time varying load, it may be because the coordinates of the sign here are shifting as it's being deformed. And so maybe when it's applying on that load, the deformed state means that you take the deformed coordinate of Z versus the initial coordinate of Z. That's my hunch. But I'd have to look it up and kind of check to make sure.
Yeah. Is the pressure, the force from the wind on the sign negative or positive, or does it matter?
It shouldn't matter because it's because it's a symmetrical in that direction.
Okay.
I did it as
positive. Okay. I just want to be consistent.
For sure.
Okay. That's all I have.
Okay, cool.
I'm looking at your the weather on your computer, 49 degrees Fahrenheit.
Oh, yeah, yeah.
Good God. I'm not nearly that cold.
That's good. That's good. 49 degrees is pretty cold. I got to walk out to my car after this, so not looking forward to that.
Okay. Thank you.
Yep, no problem. Have a good weekend, Chris.
Night.
Yeah, in terms of the changing the actual sides. Yeah, when I did that, previous measure that large, it should right back.
Yeah, because the geometry changes, so you have to recreate this.
So when doing that, do we have to like specify all of the?
Keep all the settings consistent, so use the same sizing and use the same shapes. It's gonna be a different mesh because the geometry change, but as long as the mesh sizes are roughly the same shapes, pair the two pretty much.
So in terms of like problem 5, state what the change is.
Wait, let me check and see what exactly did I ask her.
The thickness was changed by X amount.
Yes, yeah, you should say that you change the thickness by X.
Oh, no, I mean like in terms of like, since when I changed the thickness, I was using feedback and error, so I have to change the mesh.
Yeah.
I have to state that I changed the mesh.
Oh, no, you don't have to. You can just say that you kept the same mesh settings and you just had to remesh it.
We do probably want to.
Oh, no. Severino, any final questions before I wrap up the call? Okay, all right. So I'm gonna close the call. So hope you have a good weekend, and I will see you next week.